lecture on this day for the entire location Schweinfurt.
Wait. So is it just this class, or is it there's no class for all other lectures?
For all, I think so.
Oh, okay.
For all, you have to check the academic calendar. It's online. If you search for academic calendar FAWS, you get an overview over the entire semester, and there you get all exceptions, so to say, in the semester.
Okay, all right. Thank you, Professor.
Academic calendar. It's always good to take a look there, because I also went to a lecture and then I was the only person in the room because I missed some information and this was were at home and I was there. Yeah. You got an email a few weeks back about it. Okay, so you get emails. I've got no email regarding this. I have to check this by my own. But yesterday, some students remembered me in the lab that next Thursday there will be no lectures. Okay. That's for the organizational part. Then we will see how much topics I can cover today, because the next exercise sheets already go ahead with some sampler coding. Therefore, we need some more topics, some more explanations. And let's see how far we can get today. And maybe I decide this next week. Maybe we can reuse a lab or replace a lab with another lecture in the next week. But I will inform you via an e-learning notification, so you get the information in the beginning of the next week. Okay, so we have talked about in our last session about the layout of the CPU, the block diagram of CPU for an 8-bit system. And here again, you see the layout as a short repetition from last week. And yes, we have seen that the CPU contains 2 main components: the ALU, the arithmetic logic unit, and the control unit. The arithmetic logic unit is the main component that executes arithmetic and logic operations. So addition, subtraction, multiplication, logical AND, logical OR, logical exclusive OR, all of these operations are executed in the ALU. And the CU, the control unit, that's a finite state machine. In the end, we have also talked about finite state machines yesterday in our lab. Of course, the CU is a much more complex finite state machine compared to the easy ones we have seen in the lab. So the 2-bit counter and the intensity control are very easy finite state machines. But the CU, the overall structure of the CU, is a finite state machine, a Medvedev machine to be precise, and the control unit drives the entire execution in your microprocessor, in your CPU. So it starts the execution at a special address of your main memory. In general, that's hexadecimal 0. And then it starts to fetch a command, interpret the command, execute the command. Fetch the next command, interpret the command, execute the command. And if the command also needs some operands to be executed, so if you want to make an addition, for example, then you need 2 operands, sum 1 and sum 2. Then the control unit is also responsible to catch the required operands and put the operands into a specific location within your CPU. And this location, this is called a register. And the register that is used for, in the end, all operations, the most important register, that's the accumulator. The accumulator in the end stores the operands, or one operand, and after execution, the accumulator stores the result of the specific operation. The control unit also produces control signals and put these control signals on the control bus to, for example, to switch the memory to read operation or to switch the memory to write operation, whatever is in need. And the control unit also generates addresses to select a specific memory cell. We have seen that the memory cell in the end is a big table. Each row in the table is enumerated, and then if I want to read or write to a specific memory cell, I need this address here on the address bus. So the control unit knows, okay, at which position is a specific operand stored and what is the next position, what is the position of the next instruction. And this is a very important information. Where is my next instruction or where is my current instruction? And therefore, this information is stored within the program counter. So PC here means not personal computer or something like this. This is the program counter that points to the current or the next instruction. It depends on the CU. Sometimes it points to the current instruction. Sometimes it points to the next instruction. Okay. And last but not least, we want to talk about the periphery. The periphery is connected to your microcomputer via a so-called I/O port or input-output port. And here are some examples for periphery, so timers, comparators, general purpose I/O ports, analog digital or digital analog converters, USB, SATA, PCI Express, Ethernet, local area network, LAN, wireless LAN, I2C bus, SPI, RS-232, HDMI, and DVI are some common interfaces. Yeah, so RS-232, sometimes you find this interface still on a very old PC. Today it's not so often used anymore, but USB is a very common interface, universal serial bus. And we have seen on Monday in the Apple keynote that HDMI is also a cutting edge interface because it's again there in the MacBooks, but HDMI is also there for several years. Yeah, so sometimes also some old interfaces, some old interfaces are added again to new hardware, because it's so widely adopted in industry. Also at FABS, you find at each projector, at each screen, you find an HDMI port. So this is very important, despite the fact the interface itself is very old. And this I/O port, this input-output port, is also connected via the bus system to the CPU. So from the perspective of the CPU, the I/O ports are in the end nothing else than an extension of your main memory. So all ports that you can use based on this interface here get a specific address, and then you can use your bus system, your address bus, and your control lines to select a specific interface and to communicate with the specific interface. So if there is data available, you can make a read operation on the specific address, and read then means read the data from the outside world, read the data from the hardware component. And if you make a write access, then you can also send data. So for example, if you send some data to your printer via USB, you make a write operation to a specific address in your input-output port. Yeah, you can distinguish parallel and serial interfaces. And most modern systems use a serial interface. So USB, I've already mentioned this, USB stands for Universal Serial Bus. this is in the end a serial interface that you can use to read arbitrary data. So it's the most, so to say, common standard today that you can use to read arbitrary data. At the moment, we have mostly used is USB 2 point something, but USB-C, that's USB 3 point something or higher, it becomes more and more used in industry. And the problem is, or the good news is, if you use USB-C, and standard 3 point something, then you can send all data using one interface. You can send your graphical output, so your output to your screen. You can send data. You also can use it to charge your device. But the problem is, oftentimes the periphery is not supporting USB-C. So if you have a projector at the FRES, you will find HDMI port and VHA port, standard VHA port, and there is in general no USB-C port. Yeah, and then you need a special adapter. So if you have Mac hardware, you know this from the last years, you have something in your bag, a dongle, an adapter that you can also connect hardware with a different interface. Yeah, dongleware or dongleware. Sometimes you read this in the magazines, that you always have a bag of dongles in your backpack, that you can connect your hardware to some external periphery. Then there is another term, maybe you've already heard this, DMA. DMA stands for direct memory access. So for some I/O ports, for some interfaces, it is possible that the external hardware sends a special trigger signal or a special control signal to your CPU to draw attention. So, for example, if new measurement values are available here at the I/O port, then the port can use the direct memory access, the DMA, to send a direct signal to the CPU, and this signal interrupts the standard operation of the CPU and triggers a special DMA handler or interrupt handler. And this is oftentimes important. So if your I/O port, if your periphery should be able to signal a special condition, then you need this direct memory access. In Windows, you can also play around with these DMA numbers. If you go to your system control, you can assign for each I/O port, for each periphery, you can assign a specific DMA number. But be careful if you create some collisions. So if you use the DMA port, the DMA number for several I/O ports, then you're running into problems, because then the CPU cannot clearly decide, okay, which hardware needs attention. So if you work with the system control in Windows, be careful, you can reconfigure all the hardware signals in the end. And you can rewire it via software. On a Mac platform, that's not so easy, because these details are hidden from the standard user. You can take a look, but read only. You cannot modify such parameters with standard tools. In Windows, it's possible. So you can adapt to a lot of specific conditions, but you can also destroy your system or reduce functionality if you don't know what you're really doing. Yeah. So system control can be your friend or not. It depends. Okay. Good. Then we go to subsection 2.5, how microcomputers work. And here is now a detailed description how an assembler program is executed. And we go through this program step by step, and I try to explain to you, okay, what's going on here and what is done, what is realized by your CPU. Okay, so what we want to do, we want to execute this C code or C++ code. We want to store the sum of the variable x plus hexadecimal 30 to a new or to a second variable y. A simple addition. We want to execute a simple addition at the content of the variable x and hexadecimal 30 and store the result in a variable y. So the declaration of the variable, it's omitted here, it's not relevant. We simply take a look at the execution of this addition. And now we want to understand what must be realized by your CPU or by your control unit to execute this addition. And this is drawn here as a sketch, and I try to explain what's going on. You see here two components or three components. We have our CPU with our accumulator. We have our memory with some values, and we have our bus system. So what we have to do, if we want to execute this addition, we first have to execute this assembler instruction. This is an assembler instruction. MOV simply means move. And MOV, this is called a mnemonic. That's mnemonic code. So this is code that you can easily memorize. Oftentimes the mnemonic commands have 3 or 4 digits. It depends, sometimes 5. But here we have very short instructions. And this is the instruction. And this instruction takes 2 operands. The first operand is a register where we want to store a value. And the second operand, this is the value or the content of a memory cell that we want to store in our accumulator. So here it's given in words. It's still German, but I can translate. So we want to load the accumulator with the content of memory cell hexadecimal 40. So now you can ask why hexadecimal 40? Because we want to add x and hexadecimal 30. Why hexadecimal 40? And the answer is we need to know the layout of our main memory. This is important. Without this knowledge, we cannot write a correct assembler program. It's necessary that we know at which position in our memory we have stored which variable. And this is shown here. We have our memory. Here we have our addresses, hexadecimal 3F, hexadecimal 40, hexadecimal 41, hexadecimal 42. And here on the right side, there is a short note which variable is stored in which position. So we need to know that our variable x is stored in our memory cell 40, hexadecimal 40. If you don't know this, so if you have not organized or managed your main memory, then you cannot write a program. So you have to do in the end some housekeeping. You have to organize, you have to manage at which position we store which information. So we know in memory cell 40, there is our variable x. And now we copy or we load our accumulator with the content of memory cell 40. The content of memory cell 40, this is a 7F, also hexadecimal. So we load now our our content, the 7F, we load this to our accumulator A. The selection of the specific memory cell, the selection of hexadecimal 40, is realized via the address bus. So the address bus is used to select the cell hexadecimal 40, and via the control bus, it's not drawn here, it's simply the bus system, but we have the address bus and the control bus. And via the control bus, we switch this specific memory cell to read operation. So we want to read the data from this memory cell. So this is step one. Now we have the first operand of our addition within our accumulator. Questions? No? Okay. Then we take a look at the second step. Okay, in the second step, we want to execute our addition. We want to add hexadecimal 30 to the content of our accumulator. This is realized via this instruction here. Add stands for addition, accumulator, and hexadecimal 30. Please note here in front of the hexadecimal 30, there is a hash symbol, a hashtag symbol, a sharp symbol, however you want to call this. Call it a hashtag, hash symbol, and this hash symbol indicates an immediate value. Immediate value means don't interpret hexadecimal 30 as a number, as a memory cell. Don't interpret this as a memory cell, but interpret this hexadecimal 30 as a real number. As a number, so we use here the number hexadecimal 30. And here in German here is stated that we want to add the number hexadecimal 30 to our accumulator. So this can be done completely within your CPU. So we don't need a memory because we have already read our first operand. So now we add 7F hexadecimal plus 30 hexadecimal, and this will result in AF hexadecimal. Yeah, and last but not least, we have to write back our sum, the result of our addition. We have to write this back to our variable y. So now we have the same problem or a similar problem like in the first step. In the next step, we need to know where is my variable y, in which memory cell I want to store the variable y. And you can see here, in this case, the variable y is the next memory cell after the memory cell of x. So we have here memory cell hexadecimal 41. And now we have to execute the next instruction, move. That's the memory cell. And here we want to move the content of the accumulator. So this move command is similar to commands in the Unix world. So in the Unix world, you always define first the destination where I want to copy to, and the second parameter is the source. So in this case, we want to copy the content of A or load the content of A to our memory cell 41. Here we have not used the hashtag because here again we talk about the memory cell. And in words, write the content of the accumulator to the memory cell 41, hexadecimal 41. Here again, we need our address bus and we need our control bus. In the first step, we address the specific memory cell using our address bus. So we put 0x41 to the address bus. And in the second step, we use the control lines of our control bus to switch this memory cell to a write operation. That means the value AF is stored in hexadecimal 41. Yeah, and that's it. If you take a look at this mnemonic code here, move and then destination, comma, source, you can see that the oldest assembler coding is the oldest programming language because you work directly on the hardware, and because in this commands we first give destination and then we give source. You can see that the Unix operating system, that was the initial operating system, because also nowadays Unix uses exactly this notation. If you want to copy something, you give the destination and then you say, okay, where is my source? And if you use Windows and you want to copy something, then you do it exactly in the opposite way. So you give the source and then you give the destination. Yeah. So the first microcomputers, the first computers at all that were Unix computers, not Windows. Windows comes later, and to get a unique selling point or to make something different, that's always important if you want to sell something. Windows simply switched some standards from Unix. So Unix used first destination, then source, and Windows said, oh no, we do it exactly in the opposite way. First source, then destination. Or on Unix, the path separator is a slash. So there are, for example, the home folders are in /home/username. And in Windows, you use the backslash, right? So you have C:\home\users. That's exactly the same approach. Yeah? So Unix was already there, and Windows comes later, and we need a little different. And therefore, they have simply switched slash and backslash. There is no real reason for this. That's only a marketing gag in the end. It's only a marketing hint, a marketing move. Okay. Do you have questions regarding this procedure? Try to scroll out a little bit. Is this clear? Yeah. Okay. Seems to be no questions. Yeah, you can see here now that for one instruction in your C program, you need 1, 2, 3 instructions in your assembler program. And that's exactly what your compiler does for you. Your compiler takes your higher programming language program, in this case we have used C, and makes a conversion, a compilation, translation to assembler code. So one instruction in your C program boils down to 3 instructions in your assembler code. Sometimes the compiler does some magic, some optimization. So sometimes it's your code can be reduced or optimized. So you cannot say, okay, you get always the same sequence, because there are some source code optimizers in your compiler. And if the compiler recognizes an option for optimization, the compiler will realize this. So, but you see, in the higher programming language, one simple instruction is decomposed into 3 very basic instructions. And this is done for your entire code. So you can easily imagine that a code with 100 lines in C is represented with 200, 300, maybe 500 lines in assembler code, because the assembler code has in the end the same, you can compute or you can solve the same problems, but you don't have so powerful commands. So you have to express the same operation, or you have to express the same behavior with more instructions, with more commands. And this is done for you by your compiler. So you can write in your higher programming language, or you can directly write in assembler. And now we try to do some programs in assembler here in this class, that you get an idea, okay, how can assembler coding be used? Okay, perfect. Then to our next slide. On the next slide, we have exactly the same layout or the same process I have explained to you, like on the previous slide. Here we have it drawn as a diagram. Here's the program code. We have to move, we have to add, we have to move again, the result. Please note here in the example program, there is also a comment. A comment is indicated with a semicolon in assembler code. In C++, what are the symbols in C++ to add a comment? What can you use?
Use 2 forward slashes.
2 forward slashes, exactly, or
you can use forward slash asterisk and then close it with asterisk forward slash.
Exactly. Yeah. The first comment, this is a line comment. So you only comment out 1 line of code, and after the next new line, there is again standard instructions. And the second comment, this is a block comment, so you can also comment out 7 lines of code in 1 step. In our assembler programs, we only have the semicolon, and with 1 semicolon, you simply comment out this line here. So example program is not mnemonic, that's only a reminder or hint to the programmer what he or she has done here. So here, simply a note, this is an example program. Okay. The rest I've told you already on the last slide. Then, of course, we have to translate our mnemonic in the end to machine words or machine code. So the mnemonic, this one here, this is in the end for the developers. The mnemonic should be readable and writable, of course, readable and writable for developers to ease the developers' life. Therefore, we use short instructions that can be memorized very easily. And add A immediate, this hashtag is sometimes called immediate value or direct value hexadecimal 90. This cannot be executed by your CPU or by your control unit, because the control unit can only process zeros and ones. Therefore, the mnemonic code has to be translated first into hexadecimal code. So the hexadecimal code, the instruction code for an addition of an immediate value to your accumulator, this is hexadecimal 24. Hexadecimal 24. And this is at A, and this can be encoded as a machine word as 2 times 4 bits, and therefore we have 0010, 0100. This is the command we want to execute. And we need also an operand, because we want to add immediate 90 to our accumulator. And immediate 90, this is encoded as a separate machine word, and the separate machine word for hexadecimal 90, this is 1001, 4 times 0. So in the end, the mnemonic again is not executed on your CPU, because the CPU cannot read mnemonic. The CPU only knows ones and zeros. So if you want to execute this mnemonic, you have to send this bit sequence to your CPU, and exactly this bit sequence. If you change 1 bit in the instruction, you have a completely different instruction. If you change 1 bit in the operand, you will have a different operand. And another example, if you use the mnemonic inc A or increment A, then this is encoded as hexadecimal 04. You see, this is much easier than the mnemonic above, because here we don't need an operand. Increment A will not need an operand because increment is always +1. So this can be encoded as hexadecimal 04, and this is translated to 0100. So this is the instruction, the bit sequence to make your control unit to increment your accumulator. So in the end, this is a 2-byte instruction. This is a 1-byte instruction.
Sir?
Yeah.
I understand how to convert the mnemonics to machine words and the Xcode to machine words, but how can I convert mnemonics to Xcode?
To what code? What do you mean?
Mnemonics to Xcode. And how do we know that 90 is 24?
This 24?
Yeah, how do we know it's equals to 90 for the mnemonics?
That's a good question. How do you know which hex code to use?
Yeah, without knowing the machine word.
Yeah, so from here to here, this is clear, right? You can directly translate hexadecimal to binary, right?
Yes, and the mnemonics too.
But the question is how to come from the mnemonic to your encoding.
Yes.
And the answer is you need a translation table. It depends. First of all, the instructions that are allowed in mnemonics depends on your CPU. In this case, this is an 8051 CPU. If you go back to the introduction slides, you will find this as one of the first CPUs from Intel. This is a very old CPU, but therefore it's also a very easy CPU, and also the instructions are very easy. So the instructions that are allowed depend on the CPU. The translation from mnemonic to hex code, this must be given to you in a table. You need a table because the encoding depends on the CPU. You cannot derive it directly. So if this is used or expressed as 24 or as 26, that's in the end the result of the constructors of the CPU. So this has to be defined by Intel, and you need to know.
Also, in this example, the S code 24 is the same as the mnemonics 90, right?
The 24 is the same as what?
The 90 in the mnemonics.
The 90 is here.
Okay, so they are not the same.
No, they are not the same. This,
okay.
The add A is this one. This is add A, and the operand is the second byte here.
Okay.
You need 2 bytes. 1 byte to add something to the accumulator, and the second byte to express the operand. This is the second byte here. Yeah, so the 9 is expressed as 1001. The 0 is expressed as 4 times 0. Good question, huh? Further questions? Okay, so if you want to write your own assembler programs, then you need to know which instructions are allowed. So you need to know the mnemonics to write down the program. And if you want to translate this to machine code, you need a translation table. You take a lookup into this translation table, and then you know the corresponding bit pattern, and then you can write down the code. So, for example, you will see this in the lab. An exercise can be solve a problem, then you get a problem description, and write the corresponding assembler program and translate the assembler program into machine words or into machine code. You first write down your assembler code, double check if everything is fine, and then you make a translation to bit patterns for your machine word. Okay, very good. Yeah, here we have again the same program, the same example, but now we have realized this on Harvard architecture. I hope you can remember this from last week. We have already talked about von Neumann architecture and Harvard architecture, and I've told you that in the Harvard or using the Harvard architecture, we have dedicated memories for your programs and for your data. And this is shown here in the middle. We have our CPU with our accumulator. On the right side, we have our main memory for data. On the left side, we have our memory for program instructions. And now the program instructions are stored in the left memory block, and the data is stored in the right memory block. This is not valid if you use the von Neumann architecture. If you use a von Neumann architecture, the instructions and the data are stored in the same memory block. That means in the end, you have some memory cells with data, and you have also memory cells where the instructions are stored. So the entire program, all bytes that encode this program can be stored here. And maybe now it becomes a little bit clearer why I've said it's more error-proof, because for a von Neumann architecture, you need to know which memory cell stores instruction and which memory cell stores data. You, as the programmer, you have to manage this. Okay. So in our examples, we always use von Neumann architecture, but here again, a short example, how it may look like using a Harvard architecture. Okay, and that's it. And we have finally or nearly done this chapter. Here on the last slide, there is once again explained the relation between fetching and executing a command. I've already explained this or used these terms. So your control unit, your CPU, always operates in two steps. The first step is instruction fetch, or simply fetch, or IF for instruction fetch. And in this stage, the CU reads the instruction from the memory and interprets the bit pattern to make a decision which instruction is executed or is necessary. Yeah? So this means reading the instruction, and after you have read the instruction and interpreted, you can execute the instruction execute. That means then the CU creates the necessary control signals to, for example, realize an addition, or for example, to realize exclusive or for example, do something else. Yeah? So you always have two steps: fetching, execution, and so on. And if you have 4 instructions in your program, instruction 1, instruction 2, instruction 3, instruction 4, then the control unit has a schedule. That means in the end, it takes one instruction after another. And for each instruction, there is a so-called instruction cycle to make the entire interpretation. So that means reading, interpretation, and execution. And this is realized sometimes, for example, via 4 clock cycles. Sometimes you only need 3 clock cycles, sometimes only 2. So for each instruction, you need a specific number of clock cycles. Yeah? So clock cycle means here in the end, your basic system clock cycle. So if you have 3 gigahertz as a clock cycle, then you need 4 full iterations of the clock, for example, to execute instruction 3. This depends on the instruction. Yeah? So you cannot say, okay, a move takes 2, an increment takes 4, something else. Again, you have to take a look at the manual of your CPU. Yeah? So how many instructions are required? Some instructions can be executed fast, and fast means you need only a few clock cycles, for example, 2, and some instructions are executed slow. That means you need more clock cycles to interpret the command. Okay, this is also given here in the notes. Okay. And that's it for chapter 2. Do you have questions regarding the overall structure, the architecture, the mode of operation? It's important that you understood the procedure. Okay, everything's fine. Perfect. Then we go ahead with chapter 3. Chapter 3 is a real-world example for an ARM-based CPU. That's the Infineon XMC 4000. Maybe you know another ARM-based architecture. It's a little bit more famous than the one from Infineon. Yeah? So, for example, the CPU from Apple, the CPUs from Apple in your iPhones, or the CPU from Samsung in your Galaxies. These are all ARM-based microcomputers. And ARM processors, ARM CPUs are optimized for less power consumption. So they use a completely different design approach. So the initial CPUs from Intel, from AMD, and so on are optimized for performance, and power consumption is not so, or was not so interesting. But the ARM cores are optimized for use in mobile devices, and therefore they are optimized for less or very low power consumption. And yeah, maybe you have seen the keynote on Monday from Apple, where they have presented the new MacBooks, and there are several new ARM-based processors you can buy from Apple, and they get a lot of good feedback from the literature, from the online magazines, because they have done a very clever move. And I try to figure out what's the trick, because they have still low power consumption, but at the same time a very high performance. So that's in the end, they have optimized both vectors. They have reduced power consumption and they have enhanced the performance. And I've read, I don't know where, I think at TechCrunch or so, I've read that the performance of the new ARM processors nearly reach server performance. So they outperform all notebooks, all hardware out there you can buy. And in the end, they are also ARM processors. And here in this chapter, we take a look at the instruction set of an ARM processor. So I don't want to go into the details of this XMC 4000, because it's one specific use case, and you can change the use case, then you have another board. But I will go into the details of the instruction set. The instruction set is very interesting, and it's also valid, for example, for your Apple processor or another ARM processor. So we can take a look there, and you can also translate this knowledge or adapt this knowledge for other ARM processors. So we go very fast through the first slides, and then we take a look at the instruction set. Yeah, here we have some marketing slides in the beginning from Infineon, where they present their XMC 4000 family. Of course, you can buy different ARM processors with floating point unit, without floating point unit, with different memory sizes, with different clock speeds, with different I/O ports, and so on. And of course, you can buy a cheap version with reduced functionality. You can buy an extended version. And I guess this marketing slide is already outdated. So therefore we go over this. If you go to the Infineon website, you will get the current marketing slides if you want to know, okay, what's the most recent XMC 4000 board you can buy. Here is a system outline of this specific board, and here are some technical specs. For example, the data memory We have a 352 gigabyte SRAM. We have a program memory of 2 megabytes as flash. We have a CPU speed of 144 megahertz, so not comparable to your desktop PC in the end, but enough to solve most of automation problems or most of embedded problems with this system. We have 32 channel in our AD converter. We have 17 digital general purpose I/O ports that you can use to connect periphery, and that we will study in detail. This board supports the ARM SAMP1 and ARM SAMP2 instruction set. So the instruction set, this is in the end the set of instructions that can be interpreted and executed by your CPU. And the instruction set, I've said this, depends on the CPU. So your i7 supports another instruction set than your M1 processor in your Apple machine. So the instruction set always depends on the hardware, on the CPU, and ARM or this Infineon board supports 2 ARM instruction sets, SAMP1 and SAMP2. Yeah, the entire processor, that's a RISC processor. You will see later on what RISC means. RISC stands for Reduced Instruction Set Computer. So in the end, that means that you don't have a lot of instructions for very specialized tasks, but you have a very reduced instruction set, a small instruction set that can be combined or that can be used to solve the problems. Yeah, there is also so-called CISC processors with an advanced instruction set, but here this platform, this is a RISC platform. And the ARM processors are also distinguished based on their fields of application. Sometimes you read in magazines about Cortex-M processors, Cortex-A processors, and Cortex-R processors. Cortex-M stands for microcontroller. So, for example, in your washing machine, in your home automation, in your PlayStation 5. I guess the most recent version is 500. Here you will find Cortex-M. Then there is Cortex-A for application. If you want to execute more sophisticated programs, if you need more processing power, then you can use Cortex-M. And then there is Cortex-R for real-time. Real-time is always necessary if you need to define or require deadlines. So real-time is oftentimes misused in computer science. Real-time does not mean something is fast. So if you take a look or if you watch TV and take a look at the news, then oftentimes real-time is a synonym for fast, right? So the votes are counted in real time, or the sick people are counted in real time, or something like this. And then they mean they are counted fast, but fast does not mean real time. Real time means that there is a specific deadline that must be met, and you will always realize this deadline. So for example, if you are driving your car and you have an anti-block braking system in your car and you need the system. So if you brake very hard and then the system needs to react, for example, within 200 milliseconds, then you have a fixed deadline of 200 milliseconds, and whatever it takes, these 200 milliseconds must be realized, must be met, And this is a deadline, strict deadline. And here we are in a real time. And if you work on your desktop PC, then this is not real time. This is in the end best effort. So your PC tries to handle all tasks. And you know, if you have too much games running and too much videos and too much of everything, then your system slows down. It feels a little bit, or the performance is reduced, and then it feels not so fluid, so to say. And this is best effort. So the desktop PCs are created for best effort processing, and for some domains you need real time. For example, also safety circuits. If you have a safety requirement for a nuclear plant, for example, to make a safety shutdown within 15 minutes, then this is also real time, because the deadline now is 50 minutes. So real time does not mean fast, not 200 microseconds or 2 nanoseconds. It can also be 15 minutes or 2 days. The point is you need a fixed deadline. So this is real time. If you hear this term for the next time, real time, make a reality check if it means fast or if it means you keep the specified deadline. Okay. Then for programming purpose for the XMC, there is an evaluation kit. The evaluation kit is free to download and to use. That's called Dave, and it's based on Eclipse. So in the end, this is a plugin to Eclipse, and then you can use C, C++, and Java to work with this board. And yeah, you have in the end 3 compilers. One compiler that compiles C code to machine code, one that takes C++ code and produces machine code, and another one that takes Java code. So it's up to you which programming language you prefer. You can implement in a higher programming language, and this is compiled to a specific to the specific machine code. Can you send us the link? Which link? What do you mean with link? Link to what? Yeah, for Dave. Give me a second. So if you Google for Infineon, XMC, and Dave, then you will find several resources. And here, for example, this is a download page for some example projects that are already realized that you can download. And Dave is available. Dave is available here. That's the free IDE. It takes 1 gig on your hard drive. It's not so small, but it's there everything is included that you need if you want to start. Software tools Infineon.com. There you get everything you need. Okay, that's Dave. And yeah, then we have here some block diagrams about the internal layout of this board. We skip this now because it's not so interesting for our assembler coding problems. The next slide, that's more important because it outlines the differences of the different or the different architectures that you can buy or use of this Cortex processors. You see here several rectangles, several boxes, and each box represents the instruction set for one specific processor. So here the small green one is the instruction set for the Cortex M0 and M1. So you see here commands. Here are some commands highlighted with these orange boxes. You have a command for addition, you have a command for logical AND, you have a command for left shift, right shift, you have a command for move. Here's our move again. So the command move from the very early days of the AT51, it's still there. It's still called move in the assembly program. We have branch command, we have a logical OR, we have a multiplication. So we have a lot of instructions, and some of them, not all, but some of them we will study in detail today and also in the next week. And the next bigger block, that's the blue one. The blue one extends this instruction set with new commands. So for example, we have an LDR for load register. We have a pop for read something from the stack. We have a push and pop are corresponding instructions. Push means store something on the stack. Pop means read something from the stack. I'm sure you have talked about the stack in your programming class, and we have again a stack here. We have again a branching and so on. So you see that the blue instruction set is much bigger than the green one. So we have more instructions. Therefore, we can realize more complex programs in an easier way. So the green block has the same computing power as the blue one. The green one is a subset of the blue one. But with the green one, you need much more instructions to solve the same problem, because the instructions are reduced and the functionality of each instruction is reduced. Yeah? So the bigger the instruction set, the easier you can solve or implement your problems, and the shorter gets your programs. Then we have this pink one here, Cortex M4. You see a lot of commands, and the last but not least, the orange one, that's an extension for floating point operations. FPU means a floating point unit, and here you have additional instructions for floating point operations. So in the end, it depends on your hardware, which instruction set, which plane, which rectangle is supported. And of course, for you as a programmer, the more instructions are there, the more you have to know to write a specific program. Are the repeated instructions in the blue block, e.g. move knob, same as the ones in the green block? Yeah, you're right. Some commands are repeating. In the end, the green is a subset of the blue, and there are the same commands. Everything that's there in the green one is also there in the blue one. From a mathematical view, it's not set, subset, 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 because we have no duplicates in sets, right? So a mathematician will say that's not a good representation, but that are the same commands. And the semantics of the commands are the same. Yeah. You're right, Maria. Yeah. Yeah. So this figure is from a marketing guy again, not from a mathematician, not from a math guy. You're right. So as homework, you can eliminate all duplicates to make it a proper set representation, if you want. Okay, just kidding. Okay. So the next slide is also important because here are some new important terms that we haven't covered by now. I tried to highlight the most important things on this slide, where to start. First of all, we have here another block for the floating point unit. Here we have special registers that can be used for floating point operations. That means for the representation of floating point numbers, fractional numbers. Therefore, we have a block here in the middle. And during this class, we will not use it. We will not need it. So you can simply ignore this block here in the middle. It's not interesting for us. Floating point operations are, for example, very interesting if you want to do some 3D programming or something like this, or you want to do some scientific calculations, then this comes into play. But for the very basic understanding and usage of this architecture, it's not necessary. Then let's take a look. Sorry, I'm trying another cursor. Let's take a look here on this orange block. This block is very important because in our ARM Cortex-M4, we have now 16 general usage or general purpose registers. So in the last week, I told you there are two special registers in the ALU, the accumulator, and the accumulator or the accumulators are used to add two operands or to combine two operands. And therefore, if you want to execute an addition with 3 or 4 or more operands, you have to do it step by step. If you only have 2 registers in your CPU, in your ALU, and you have 1 plus 2 plus 3, then you cannot move all operands at the same time to your CPU. So you first have to execute 1 plus 2, and then this result plus 3. Because you don't have enough registers, you don't have enough memory cells to handle intermediate values or to handle the operands. On this platform, we have 16 registers. So we have a lot of registers that can be used for arbitrary operations. So we can, for example, make a logical AND of R3 and R6, or we can make an addition of R0 and R1. That's up to you. You can use all of them. So this eases your programs because you can now store intermediate values or partial results here in the registers. R13 has a special meaning. R13 is used as the stack pointer. So here you have the address due to the topmost position in your stack. So this should not be used for calculations, for general calculations. Here you store the topmost position of your stack. And then we take a look here at the right side. So I'll take another cursor again. I take this block here. Let's take a look at the right side at this so-called APSR. The APSR is the so-called Application Program Status Register. Application Program Status Register. You see here, this is a 16-bit register. The bits are enumerated from 16 to 32, and only 4 bits out of the 16 bits are used. The bits 16 to 27 are simply a 0, but bit 31, 30, 29, and 28, they have special functionality. And before I can explain to you what does this mean, I need to explain to you what's a so-called flag, a status flag. I search for the term here. Is the term also here? No, but I explain it here. So within your CPU, there are some so-called flags. Flags, in German Flagge oder Hinweis, are used to signalize a special condition. So the control unit uses these flags to make a decision how to proceed with your program. And these flags are very, very basic. And the common flags that are used nowadays are N, Z, C, and V. N is the negative flag. So if this bit 31 is set to a 1, then the last operation has produced a negative result. So if you calculate 3 minus 5, then this is done via 2's complement. The result is minus 2. So your last operation has produced a negative value. And this is indicated via a 1 in the negative flag. If you then execute with the next instruction, 1 plus 1, this addition produces a positive number, not surprising. And then the negative flag is set back to 0 again. So for each instruction that is executed, all flags within your CPU are modified. In general, there are exceptions, but in general, for each instruction, all flags are modified, and the modification of the flags indicate the status of the CPU after the execution of the last instruction. Then we have a Z flag. Z flag stands for 0 flag. This indicates the last operation produces a 0. So if I execute now, for example, decrement DEC of 1, this is a 0, right? Decrement of 1 is a 0. Then the 0 flag is set to 1 to indicate the last operation produces a 0. The negative flag, which value is stored in the negative flag?
It'd have to be a 0.
It's again a 0.
Wouldn't it?
Exactly, because it's not negative. 0 is not negative, so I store a 0 here. Then we have a C flag. This is a carry flag or a borrow flag. This indicates that the last operation produces a carry or a borrow, depending on the operation. So, for example, if I add 2 numbers and I've got a carry to the next position, then this is indicated via a 1 here. And so this depends on the numbers that I add and the size of the registers or the memory cells that I use. So this is very dependent on the operation and on the memory layer. And there is an overflow flag that indicates that I've reached the limit of a specific number range. So for example, if I add +1 to the biggest integer that can be represented, then I get the smallest negative integer, and this is indicated via a 1 in the overflow flag. So why do we need this 4 bits? We will see in the next week, because we have only a few minutes remaining, but in the next week, we will see that these bits are used to make a decision during the execution what to do next. So for example, you use these flags to make a decision for an if statement, or you use these flags to make a decision in your while loop, do another iteration, or just leave. And these flags are very, very important. And it's important that you understand the purpose or the usage. So you as a programmer, you can only read the flags and make a decision based on the value. And the control unit modifies the flags. It's done automatically. You cannot modify this or handle this. So you make an execution, and after execution, you get a new bit set in your APSR, in your status register. Okay. Then here on the right side, we have the memory layout. I scroll in a little bit. Maybe we can read it. Okay, it's possible. Here you have the entire memory layout. That's similar to the very simplified representation we have seen the last week. We have the addresses here on the right side, and you see the different segments, the different blocks. Here at the bottom, we have 0.5 gigabytes for the initial code. Then we have a block for our static RAM. We have some block for the periphery. So this block is used to access the periphery via a specific address. Then we have external RAM. So this is a RAM that can be extended and then can be referenced via this block. We have some addresses for external devices. This is comparable to the periphery here. I'm not sure why they make a distinction, but in the end, this is also from the perspective of the CPU periphery. Then we have some private peripheral bus, and we have some device space. So now to get the exact meaning of each block, we have to take a look at the manual. But you see here the same structure. We now know, okay, which memory block should be used for which purpose. And this is directly taken. This is directly taken from the manual. Yeah? So if you now ask, okay, how do you know, or how to get this information? Yeah? You buy the CPU, and then you get, hopefully, a good manual, and in this manual, all technical specifications should be explained. Memory layout, register layout, which flags are there, how these flags can be used, which instructions are allowed, how are instructions encoded. Okay, so I've explained this to you, and this is the last slide for today. Yeah, this is the last slide for today, because then we have a good starting point in the next week for our exercises. Then we can take a first look. I think it worked, but we do this slide and then we stop. For the moment, ignore little endian memory model here at the top. I will explain this in our next lecture. This is not so interesting, but here at the bottom, this is very important also for the lab, because here we have some examples and how these instructions are interpreted and executed. Move R0, R1 can be written with some symbols like this. The content of R1, the register R1, is copied to the register R0. You see here again, first destination, then source. So R1 is the source, R0 is the destination. Then we can make additions. If we write add R0, R1, R2, then we add the content of register 1 and the content of register 2, and the sum is written back to register R0. We can also do a subtraction. If we write sub R0, R1, immediate 1, that means subtract the number 1 from R1 and write the result back to R0. You see here again this hashtag that means intermediate value or intermediate number. And now that's important. These instructions are executed within your CPU. So here we have direct execution or direct addressing. With using these instructions, you don't use your memory at all. All of these instructions are executed only within the CPU with registers and immediate values. The second block gives some examples for offset addressing. And offset addressing means read data from the main memory. It's comparable with pointers in C++. For example, if you write LDR, that means Lord register, R0 brackets R1, then this can be written as M of R1 written to R0. And M of R1 means I want to read the content of memory cell R1, or I want to read the content that is referenced by memory cell by this register R1 and write this back to R0. So that means I take a look at the register R1, there is a value 42. And then I use this 42, I interpret this 42 as a memory cell and making access to the memory and read the data from the memory and store it in R0. So this is indicated with the brackets. If you see brackets, that means go to the memory. Another example, LDR, R0, brackets R2, immediate 4. This means take the value in register R2, add 4, take this value as a memory cell, read the memory cell, and write the content to R0. You can also do this with two registers. You can say LDR R0 brackets R2 R3. This means take the number, the value of R2, plus the content of R3. This will produce a number. Use this number to make a memory access and read this content to R0. And last but not least, for today, I use some parentheses here because this is a very special example. You can use LDR R0 brackets PC immediate 4. This means you take the content of your program counter. So this is your next instruction. Add immediate 4. Use this as access value to the memory and then read the command or read the content to R0. So this is in the end manipulation or use of your program counter, but we will not cover examples with the program counter where this must be modified. So for me, it's important that you know the difference between direct operations in your CPU and offset addressing using this bracket notation. Okay. So I'm 1 minute too late, sorry for this, but I think now we have a good starting point to work with the exercises. So a short preview for the next or to the next week, we take a look at the execution of some example instructions, and then we have a lot of hard copies from the manual of the XMC board. So these are the originals from the manual, so given to us by Infineon, and I will discuss with you the most important commands, how they are executed, how they are interpreted. So we will not cover all commands, but I give you the most important that you will be able to solve most of the problems that we will cover in this class. Of course, you can solve all different problems, but I show you the commands that will ease this, that you get fast results. So a lot of manual pages. I will focus on specific ones, and then after this chapter, you know how to write code for this XMC. That's all for today. Thank you very much.
Okay, thank you, Professor.
Dankeschön. Tschüss.